Alright now, so much for stellar evolution. Let's spend the last little bit of time of this lecture talking about the evolution of the entire universe, in other words, cosmology. Our universe, does it have a beginning? Does it have an end? Does it have infinite size? The most astonishing revelation about the evolution of the universe was the so-called the Big Bang theory, and it originated from the observation of Edwin Hubble. Edwin Hubble was a local astronomer, local to Southern California. During the year 1928 through 1936, he used the 100-inch Mount Wilson telescope to observe galaxies and stars. And what he found through the study of the spectroscopy using the gravitational redshift, basically, you observe the frequency of the light coming from those stars. You find, the frequency gets lower. It was shifted towards the red color of visible light, and he interprets it as a movement of that star away from us. Okay, so basically Doppler effect. He painstakingly studied the redshift of many galaxies, and he found this astonishing connection between the speed of a galaxy moving away from us and the distance of that galaxy relative to us. That's r. He found that if you double the distance of that galaxy to Earth, the speed of the galaxy leaving us also doubles. There's a linear relationship. It's called Hubble's law. I once went to the Mount Wilson Observatory. I looked at Hubble's chair underneath the giant 100-inch space telescope. This was where he made this astonishing discovery. And here you have what's called Hubble constant, which relates the speed of a galaxy moving away from us, and r, the distance of that galaxy to us. Now, you might think that because everything seems to move away from us, that we are at the center of the universe. That is not true. The universe does not have a center. Okay, it doesn't mean anything like that. For example, if you had a balloon, right? You had a balloon, spherical balloon, and on that balloon you have a whole bunch of polka dots. The distance between polka dots, whatever it is. Now, as we expand that balloon, make it bigger and bigger, what happened to the polka dots? Well, the distance between every polka dot to every other polka dot is increasing. If you use this polka dot as a reference frame, everything is going away from us, from that dot. Or if you use that dot, you get the same thing. Okay, every dot is moving away from this one. It doesn't mean this dot is anything special. It doesn't mean the Earth is at the center of the universe. Okay, so here's the thing. If the universe is expanding, as we trace back in time, did it mean the universe was very small to begin with, or even was a point? Well, this is the origin of the Big Bang theory. In fact, the further a star system is away from us, the faster it leaves us. What if V equals c? That is as far as it gets, right? This r will be r maximum, because anything further than that will have traveled faster than speed light, which is not possible. So let V equal to c. So c equals h times r maximum. This is the edge of the visible universe. And then suppose this expansion went on with a speed c, approximately, for a long time, t. Then t equals r maximum over c, right? So basically that's the time it takes for the most remote star system to expand to today's distance. And then you do this calculation, this is just 1 over h. Okay, it's just 1 over h, and h, in the Hubble constant, there's a light year here, because that cancels with that r distance in light years, out of convenience. We need to change that light year to meters. So 1 light year is 9.5 times 10 to the 15 meters. We do this calculation, you get time. This time is 9 times 10 to the 17 seconds. That's a crude estimation. I mean, the order of magnitude is correct, 10 to the 17 seconds. This is the age of the universe. So 10 to the 17 seconds ago, what happened? People believe, scientists believe, it was the Big Bang. That was the beginning of space and time. Everything in the universe came from one point at that moment. It's one of the most craziest theories in science, or in any human knowledge for that matter. Such a crazy science, crazy assumption. You have to have concrete evidence to support it, otherwise people are not going to believe it, right? here comes one of the most critical piece of evidence to support this crazy theory, and it's a so-called 3K cosmic background radiation. That's a remnant of the Big Bang. You know, when you expand something hot, as it expands, it becomes cooler and cooler and cooler. The same thing can be applied to the universe, to the entire universe as the Big Bang. Initially, the temperature was enormously high, okay, as the universe was extremely condensed. And then as it expands and expands and expands, it cools down, cools down, cools down. At today's, if you consider, you know, the expansion taking place 10 to 17 seconds ago, people can calculate, scientists can calculate what kind of temperature the universe should have already cooled down today. And what they found, the temperature should be around 2.7 Kelvin, okay, 2.7 Kelvin. That is the temperature of the universe today. Is that true? Well, two scientists, Penzias and Wilson, scanned the sky in various directions, and they found this radiation profile centered at this wavelength, about 0.1 centimeters. This is microwave. And this profile corresponds to the black-body radiation profile for an object whose surface temperature is about 3 Kelvin, or 2.7 Kelvin to be exact. So, the radiation that people observed in microwave range, primarily in microwave range, gives us the supporting evidence that the universe today has a temperature around 3 Kelvin. So we call it 3K cosmic background radiation, or microwave radiation. There are other things that scientists have done to verify the accuracy of the Big Bang theory. So despite its craziness, the Big Bang theory is well received in the scientific community. We believe that this is how the universe was created. Okay, but what about the future? What happens next? The universe is expanding as we speak. Will the expansion go on forever, or will it at some point stop? And worse yet, will it someday stop and then reverse itself to eventually cause what's called a big crunch? Okay, not a Big Bang, but a big crunch. Let's see here. There is one critical piece of data we need to predict what happens, and that is the mean density of the universe. Basically, gravity is an attractive force. If you have sufficient matter in the universe at sufficient density, the gravitational pull, the gravitational attraction will stop these particles from expanding, the galaxies from expanding. Eventually will slow it down, stop it, and even bring it back. Okay, so really it's a matter of gravitational pull against this expansion. We can find the escape velocity of an object of mass m from a region, a spherical region of radius r. Okay? This is the escape velocity, very easy to calculate. We're just doing estimation here. And this mass is the mass of the spherical region. It is equal to density times volume. Now, if the escape velocity equals this, you barely have enough energy. This particle of mass small m will barely have enough energy to escape. So if we make this equal, okay, that means the universe will have a density which is just barely enough to allow expansion to go on. This is called a critical density of the universe. Okay, so the universe can expand to infinity. Any density that's higher than that means there's enough matter to reverse this expansion. So at some point it will come back because it cannot expand to infinity. This is the velocity capable of escaping to infinity. Okay, so we calculate this rho, right, plug this m equal to rho v here, calculate this critical density, and we get v over r. V is h over is h times r by Hubble's law, so that r and r cancel. That's really nice. You get a constant, okay, 3h squared over 8 pi g. So there's Hubble constant. There's, of course, the universal gravitational constant, and turns out this is the critical density of the universe. In order to stop the expansion at some point in the distant future, you must have this density. This is about 6 hydrogen atoms per cubic meter. Okay. Do we have enough density in the universe to match this number? Well, if you only count the matter that illuminates, that produces light for us to see, That is a lot less than that. It's 5 times 10 to negative 36. So we're looking at, we're looking at 9 orders of magnitude less. Okay, that's not nearly enough. But then you add all these matters that do not produce any radiation. They're dark. You add them up, even though they're dark. It's still evidence for us to see their existence. For example, you can have a star revolving, around another massive object, even though that massive object do not radiate any energy. By looking at how the star moves, we can get a clue how much mass there is by Newton's law of universal gravitation. We did all that. We added all these matters into consideration. We still find that we only have about 10% of the critical density of the universe, which means that if we did not miscount anything, if we did not leave any mass out, then the universe will keep on expanding forever because we're still off by a factor of 10. This does not mean that our conclusion is true, because we could have missed a lot of matter, so-called dark matter, that we did not count. So, what is the fate of the universe? It is still an open question. Finally, the connection between particle physics and cosmology. In particle physics, we strive to write a unified theory that explains all the interactions under one umbrella. And it turns out that was not easy. The only partial success we had was to unify electroweak interactions. So electromagnetic force and weak force really became the same thing. But that is under extraordinary circumstances, very, very high energy. Okay? Now, the universe, when it began the Big Bang in the early stages, the energy density was really, really high. So people believe that back at that time, all the 4 interactions were really the same. Today we have 4 interactions: gravity, strong, weak gravity, weak nuclear, and electromagnetic. There are 4 distinct forces. But people believe that in the beginning, right after the Big Bang, there was only one type of interaction. And as it cools down, as time progresses, okay, 10 to the negative 40 seconds, by the way, this is seconds, okay, 10 to the negative 40 seconds, gravitational force becomes different from the other 3 forces, today known as strong, electrical, strong, weak, and electrical. And then as time progresses any further, gravity is still gravity, but within this branch, is strong force is split from the rest. The rest is weak nuclear force, which then split further. We're talking about a tiny, tiny fraction of a second. Okay, look at this. This is 10 seconds. So 10 seconds, 1 second. 1 second after the Big Bang, we already have these 4 distinct forces. All right, so we're talking about the study of an enormously small fraction of a second right after the Big Bang. So there is a connection between particle physics and cosmology. In cosmology, we want to know what happens, as the universe evolves. But in particle physics, we want to write our theory from here to there. And you see this connection here? In today's particle physics, we are building bigger and bigger particle accelerators. Why are we doing this? Because we want to mimic the condition at the early stage of the universe, where these forces can be recombined to form one. That's the theory of everything, of course. So that's the natural process is that the single interaction splits into different branches over time. In particle accelerators, we want to take the time backwards. We want to create this high energy environment where these branches merge together, so we can test our theory of unified description. So this is an incredible study that encompasses pretty much everything. There's time, there's space, which is the entire universe, there's ultra small particles, and ultra large, which is the entire universe. And once again, only in physics can we do that. So that is our overview of modern physics. That is our Physics 1D. It has come down to an end in this lecture. I hope that I have given you an idea of how modern physics, the basic ideas of modern physics, and I hope that I have raised more questions than answers in this, because I would be totally wrong if I told you that, okay, this theory is perfect and we understood everything. As you can see here, there are a lot of open questions, especially in this chapter. Okay, when it comes to quantum mechanics, the conceptual stuff is not easy to grasp. So if you're confused, that's great. That means you are getting into it. Okay, Niels Bohr once famously said that if you think you understood everything after you study quantum mechanics, that means you understood nothing. Okay, you're supposed to be confused because that gives you an idea of what further you should think about what really goes on in the microscopic world. So, hope this is only the beginning of your study of the microscopic world as you apply it to areas such as microelectronic circuitry and telecommunications, even nuclear energy. There are a lot of things, pretty much all modern technologies connected to modern physics. So hope we enjoyed it. Thank you very much.